Hi guys, 2.6 rational functions and their graphs. We're going to be dividing this lesson into two parts, objectives 1 through 5, and then in a second assignment we'll do objectives 6, 7, and 8. Okay, so the domain of rational functions, I'm going to be talking about that within vertical asymptotes, just so you know. We're going to start with arrow notation and objective 2. We used arrow notation just a little bit in Algebra 2 when we were talking about the end behavior of a polynomial equation. So we would informally say up, up, or down, down, or down, up, or up, down. But formally, we would say as x approaches a certain value, the f of x, or y, approached a certain value. For end behavior, it's as x approaches infinity, f of x will approach a certain thing. With rational functions, we have something different. We don't have that polynomial behavior where we would have up, up, and down, down, or down, up, and up, down. Instead, as x approaches infinity, okay, y is approaching a certain value, and that value is 0. You can see it leveling off toward the x-axis, and remember the x-axis has a y value of 0. Okay, so we could say here would be an arrow notation. You wouldn't always have to put increases without bound. It's just putting that in there to help you understand what infinity means. Okay, the new notation we are going to see, though, is what we see up here in the top. Okay, and I'm going to talk about this one first. No, I'm going to talk about this one first, I think. As x approaches 0, that's the way you read that. As x approaches 0 from the negative side, that means you're approaching from the left. So I put my mouse here on the left side of my screen, and I'm going to slide on the graph approaching x equals 0. And the closer we get to x equals 0, the more up this graph goes. That means as x approaches 0 from the negative side, the f of x is approaching positive infinity. It's going up. Approaching 0 from the positive side means that we're going to start over here on the positive side, and we're going to go backward towards 0. And again, for this particular graph, it's going up toward positive infinity. Okay, you have this arrow notation chart in your book that says as x approaches a from the positive side, that means x is approaching a from the right. And as x approaches a from the negative side, it means it's approaching from the left. If x is approaching infinity, that means it's going all the way to the right. And if x is approaching positive infinity, it's going all the way there to the left. You have a couple of problems on your assignment set, on your problem set, that ask you to identify arrow notation. There aren't any examples or specific checkpoints other than what I've shown you here. You can look in your text and do an odd problem, find an odd problem like this, and that will match up with what you're going to see on Math Excel. Okay, let's talk about vertical asymptotes. Vertical asymptotes we had in Algebra 2, they come from x values that are undefined or cause the function to be undefined. Okay, I told you I was going to talk to you about domain alongside this, and these functions should look pretty familiar from example 1. But vertical asymptotes happen where we have domain issues. Remember, we have domain issues when we have x's that will make our denominator 0. Okay, so the a and the b have the exact same denominator. So they're going to have the exact same domain. That does not mean that they will have the exact same vertical asymptotes. Let me show you what I'm talking about. When we go into part A, f of x equals x over x squared minus 9. We can factor that. The factoring is what will allow us to find those zero denominators. That will tell us what the domain is. That will also tell us what the vertical asymptotes are. Vertical asymptotes specifically, x cannot be -3 for the first factor, x cannot be +3 for the second factor. And those right there, writing x equals 3 and x equals -3, those are the equations for our vertical asymptotes here. You can see this on the graph. So x equals -3, here's a vertical asymptote, and x equals +3, there's a vertical asymptote. Okay, if we want to talk about increasing, decreasing, or the arrow notation from the previous objective, we could say as x approaches 3 from the positive side, f of x is going to infinity. Where is f of x going if you approach 3 again, but from the negative side? That would be -infinity. Okay, let's take a look and see how b is a little different. With b, we still factor, and we still have this x plus 3, x minus 3. But because we have x plus 3 top and bottom, we can cancel that out. And so the simplified version is 1 over x minus 3, and it says provided, and a lot of times we leave out that word provided, x cannot equal -3. Okay, so this denominator would be 0 if x was equal to +3. That is where our vertical asymptote is. But what about the -3 that we had in part A, and this provided that x equals -3 here? Okay, where does that come from, and how does it show up on the graph? Okay, this comes from the original problem. -3 was not possible. G of x equals x plus 3 over x squared minus 9. X cannot be -3 for this before it was simplified. Okay, after it was simplified, -3 is not a problem. So what we have when we graph g of x, the function we started with, is we have the vertical asymptote where x is equal to 3, but where x is equal to -3, we actually have a hole. You probably didn't even see it the first time. That hole is where x is equal to -3, and it's actually where y is equal to -1/6. We get the y value by putting the -3 in here to the 1 over x minus 3. Pause this, go back, look at it again, ask me a question if it's not perfectly clear, okay? All right, let's look at part C. Part C has a little typo that you need to be aware of. I have it correct here on my screen, but in your book it may not be correct. So check that in this solving part of part C. Okay, it says here, if we've talked about factoring. X squared plus 9 is a sum of squares. And we talked in Algebra 2 and even earlier this year about how a sum of squares cannot be factored. Okay, so just because something can't be factored does not mean we won't have any vertical asymptotes. But if you have a sum of squares, you are never going to be able to have a denominator of 0. You're going to take a number, you're going to square it, and it will be 0 or positive, and then you're going to add 9 to it. So the smallest the denominator could be is 9. Okay, and you can see this kind of funny shaped graph that we have here in part C. All right, no vertical asymptotes there because nothing would make the denominator 0. Thinking back to example 1, objective 1, finding domain. If nothing will cause this denominator to be 0, then we have no domain issues, and that domain would be -infinity to +infinity. One more quick example on horizontal asymptotes. f of x equals x squared minus 4 over x minus 2. The denominator is 0 if x is equal to 2. So that is excluded from our domain. I want you to think whether or not this positive 2 will produce a vertical asymptote or if it will produce a hole. I'm going to go ahead and continue. If you need to pause, go ahead and pause. Okay, so when we factor this, we see that the x minus 2's cancel. Remember, that's what we call a removable discontinuity. If it's removable, then that means that x equals positive 2 produces a hole in the graph. Okay, so here's where x is 2, and we have this hole in the graph. I wonder if any of you are kind of surprised that x squared minus 4 over x minus 2 makes a straight line. Remember that if you take a quadratic and divide by a linear, you have a linear. And a linear function is a straight line. So this is a straight line with a hole in it because those x minus 2 factors canceled out. Okay, horizontal asymptotes are new for us. Horizontal asymptotes focus on that arrow, arrow notation as x goes to infinity. A horizontal asymptote is asking us on the ends, on the end behavior, is it leveling off instead of with polynomials going up and out forever or down and out forever? Is there a leveling off? Okay, so here we have an example of where the horizontal asymptote is leveling off to a y value of b as x goes to infinity. And here we see it still approaching b, but this time coming from the top side. It doesn't matter which side it comes from, just that it's leveling off and what it's leveling off to. This is showing you that sometimes, unlike a vertical asymptote, you might have a graph crossing over your horizontal asymptote before it levels off. Horizontal asymptotes are focusing on end behavior. I'm going to show you how you can know from an equation, from the function, if something's going to have a horizontal asymptote or not. Sometimes they do, sometimes they don't. Okay, so here's example 3. I have a graph of part A, f of x equals 4x over 2x squared plus 1 shown on the screen. What you're going to hear me say is you are going to hear me call this a bottom-heavy function. A bottom-heavy function is a function where the denominator's degree squared is more than the numerator's degree first power. So what we do to account for that is we are going to have the squared in the numerator as well as the denominator. Okay, so instead of just saying the numerator is 4x, we're going to balance this degree and say 0x squared plus 4x over 2x squared plus 1. The horizontal asymptote happens at 0 over 2, or y equals 0. Okay, it's the 0 over 2. And so you can see we've only gone -5 to 5, but it is starting to level off toward the x-axis, which is a y value of 0. Stick with me through parts B and C, and we'll see if we can't get this whole bottom-heavy issue and this where I got the 0 straightened out, okay? All right, going on to part B. G of x equals 4x squared over 2x squared plus 1. You'll hear me call this a balanced function. And it's balanced because the numerator's degree and the denominator's degree are the same. Okay? All right. So the numerator, we have this 4 over the 2. That's how we find the horizontal asymptote for a balanced rational function. It's the ratio of the leading coefficients for the numerator and denominator. So 4 over 2 is 2. Okay? In the previous example, I had done 0 over 2 because we had to add this 0x squared into the numerator. Let's take a look at part C. Part C, 4x cubed over 2x squared plus 1. If you look at the graph, we don't see any leveling off, and you can see it says this graph has no horizontal asymptote. You'll hear me call this not bottom heavy, not balanced, but top heavy. Top heavy meaning that the cubic in the numerator is of greater weight than the squared in the denominator. So just like in the first part A, I added a 0x squared to the numerator. Here I'm going to add a 0x cubed to the denominator. So we, to find our horizontal asymptote, are going to be taking 4 over 0. And 4 over 0 is actually undefined. So if you have something that's top heavy, you're going to get this undefined ratio, which means we're not going to have any horizontal asymptotes. Okay. So go back through. Bottom heavy, you will always find that a bottom heavy function will have a horizontal asymptote of y equals 0, the x-axis. A balanced function will always have the horizontal asymptote that is the ratio of those two numbers, 4 over 2. And a top heavy function will never have a horizontal asymptote. There will never be that leveling off toward the infinities. All right, just one more thing, and you can get started and finish this entire assignment. Using transformations to graph a rational function. We've talked about how to take a parent function and modify it based on transformations to get the new function. Okay, so here we're going to start off with the graph of f of x equals 1 over x squared. That's what this is. Okay? We're going to use that to get a graph of g of x equals 1 over x minus 2 squared plus 1. Okay, so the 1 over x minus 2 squared. Notice that we are subtracting 2 inside the function. By inside the function, I mean inside the rational and inside that denominator, that squared. So the effect that that has is to shift the curve to the right 2 spaces, okay? So instead of the vertical asymptote being where x is 0, we have a vertical asymptote where x is 2. Okay, now the plus 1 was added outside the function. And if we add 1 outside, it's going to cause a vertical shift. So we now have this vertical asymptote still where x is 2, but the horizontal asymptote has been shifted up 1 space to where y is equal to 1.